shape, right? And those are related to molecular shape because molecular shape is related to the properties of the molecules themselves. And let me make sure I don't lose my charging cable again. I didn't. All right, so what were the different intermolecular forces that we talked about? What's it? We have hydrogen bonding. Yep, we have London dispersion forces. And what was the last one that we had? Dipole-dipole interactions, right? Dipole forces. And so we'll start from weakest to strongest. What's the weakest of the intermolecular forces? London dispersion forces, right? So this was the weakest intermolecular force. And what caused London dispersion forces? Or what's the origin of London dispersion forces? Anything with electrons, because anything with electrons, right? Because what happens with these electrons? What's created? A charge differential within the atom or molecule, right, which creates a temporary dipole in that molecular atom, right? The electrons can slosh around. When they slosh around, they make the electrons in the molecule next to them slosh around, and those kind of synchronize together, right? They go back and forth, and they create a force of attraction between the two molecules, right? So this is from, I'm going to use the sophisticated language, transient dipoles. Transient dipoles, all that means is just temporary dipoles, right? Transient just means it exists for a short period in time. And it sounds cool, so I like to use that better. All right, so that was our weakest intermolecular force. And then also for London dispersion forces, how do we scale those forces? Right? What makes it stronger or weaker? What makes London dispersion forces stronger or weaker than other London dispersion forces? It is because they're temporary. But what properties of the molecule or the atom, I'll put two apostrophes, make them stronger or weaker? The bigger the atom and the larger the molecular weight of the molecule, right? So the bigger the molecule, the stronger they are. The bigger the molecule, the stronger the forces. Right, so if you have an atom that has 1 carbon and 4 hydrogens, sorry, a molecule with 1 carbon and 4 hydrogens, like methane, so CH4 versus C2H8, right? This molecule on the right is going to have larger London dispersion forces because it's a bigger molecule, has more electrons to slosh around, which means the temporary dipoles can be larger, right? So this would have larger London dispersion forces. What about the strongest intermolecular force? Which one was that? This one was hydrogen bonding, right? This was the strongest. And what was required for hydrogen bonding? Yep, we need hydrogen, right? As the name would suggest. So at the very least, we know we need hydrogen. We need hydrogen bonded to one of what 3 elements? Yep, to fluorine, oxygen, and nitrogen, right? So the way you can remember this is hydrogen bonding is FON, right? It's FON, like it's fun, but it's FON, right? Fluorine, oxygen, and nitrogen. And that's our strongest intermolecular force. And that's because this is a very specific type of dipole that's formed. Those are very electronegative elements, which means they pull electrons very strongly. Hydrogen only has 1 electron on it, so it pulls that 1 electron very, very strongly. It creates a very large dipole. So those are special dipole forces. And what about dipole-dipole forces? That's going to be in the middle in terms of strength. And what gives us dipole-dipole forces? That's exactly right. Molecules with permanent dipoles, right? So molecules with permanent dipoles, right? That means they have a permanent dipole and there's a permanent imbalance of charge. And so what's another way of phrasing a molecule with a permanent dipole? How else could we classify that molecule? It would be a polar molecule, right? So this is just another way of saying polar molecules have dipole-dipole forces, right? So those are just polar molecules. And that's whenever we have a molecule that's polar, which depends on its shapes and the bonds within that molecule, right? So the type of shape it forms and the bond that exists in that molecule, the bonds that exist, right? So usually you need polar bonds and you need polar shapes, like trigonal pyramidal or bent shapes. But you can also have tetrahedral, trigonal planar, linear. Those can all be polar as well if we have unequal sharing in opposite directions, right? So an example of that was something like carbon dioxide, except we replace one of the oxygens with sulfur. And now the dipole isn't the same in both directions because oxygen and sulfur have different electronegativities, right? So they don't cancel out. We have a permanent dipole in that molecule. All right. So those were all the intermolecular forces that we spent all last lecture talking about after we reviewed molecular shape, right? Are there any questions on any of these? And then we talked about one class of molecules that's stronger than the intermolecular forces are stronger than any of these interactions here. And what was that? Ionic compounds, right? And that's because ionic compounds have a full transfer of charge, which means you have the largest dipole possible, right? So ionic compounds were greater than covalent compounds. And we had that kind of what seemed like paradoxical statement that ionic bonds are weaker than covalent bonds, but ionic compounds, intermolecular forces, are stronger than covalent molecules, intermolecular forces, right? Because we're not talking about how the atoms within a molecule interact. We're talking about how molecules interact with other molecules. All right. So we'll start with an example, right? So predict the order of increasing boiling point for the following compounds, right? So that means you need to understand the shape, the different bonds that form, and you need to know the Lewis structure to be able to get the shape for these different molecules, right? So especially kind of from this point on in the class, everything just feels very, very cumulative because these types of things are going to be assumed that we understand how to do them at this point, right? So if we're still thinking about how do I draw Lewis structures, now would be a good time in this weekend to kind of catch up and make sure you're all up to speed because in the future, these things are just going to be assumed to be understood. All right, so the way we approach this problem is the larger the intermolecular forces, the larger the boiling point. Why? Because if the forces between molecules are stronger, it'll be harder to pull them apart from each other, right? Which means you need to put more energy into pulling them apart, which means that you need to go to higher temperatures before they start to boil, right? So that's the general strategy. What do you think the trend would be for freezing point or the fusion point for these compounds? It will be the opposite trend, right? If we have harder molecules that are easier to pull apart, that means they're going to have a lower boiling point. It also means they're going to have a lower freezing point as well. All right, so I've got a bunch of guys spend, let's do like 3 minutes, see if you can rank these in order of from lowest to highest boiling point. Order of operations for this is Lewis structure, shape, than intermolecular forces. The first thing that we should look at when we're ranking the boiling point of these compounds here. We should do the Lewis structure first, right? But even before we look at the Lewis structure, what's one thing that should jump out at you and you say, okay, well, this gives me at least one molecule's position no matter what? It's not going to be hydrogen. Well, when we draw the Lewis structure, we'll see why it's not going to be hydrogen. So, H2O will be, relatively up there. But H2O doesn't necessarily jump out at us. There's one molecule here that's different from the other ones, okay? H2, so H2 isn't the one that should necessarily jump out to us. It could, just for, it might be easy for us to analyze.
Is it potassium?
It should be potassium bromide. Why should it be potassium bromide? Because it's an ionic compound, right? Which means ionic compounds are always the strongest, no matter what, right? So it's the only compound that's ionic. So we know potassium bromide, even before we look at Lewis structures, if we try to draw a Lewis structure, it wouldn't even make sense for potassium bromide, right? Because it transfers electrons, right? This is ionic, which means that it's the highest boiling point, no matter what, right? So we know that KBr is going to be the largest boiling point, right? So that gives us one end of the spectrum already, right? So that's one way we simplify the problem right away. Easy points immediately. We just identify that this compound is an ionic compound. Ionic compounds always have the largest intermolecular forces. Now we start going through the Lewis structure, the molecular shape, and then the intermolecular forces from there, right? And so a couple people brought up H2. Where would you guys place H2? Those of you that brought it up right away. Third, second. Let's draw the Lewis structure for H2 first, right? What does H2 Lewis structure look like? H, right? One valence electron each, right? So when they form a bond with each other, what do? They each donate one electron into a covalent bond with each other, right? So H2 just looks like that. What shape is that molecule? Linear, right? Because there's only two molecules, two bonding pairs. There's no central atom, right? So it can only be linear if we have two molecules, right? And is it a polar molecule? No, why not?
It's balanced.
Because, yeah, you have equal electronegativity in both atoms. It means they share electrons equally. So that's going to be nonpolar. Polar. Some people may have thought hydrogen bonding with this, but why can't there be hydrogen bonding here? Even though we have hydrogen, right? Yeah, there's no fluorine, oxygen, or nitrogen that it's bonded to, right? So there's no, remember, hydrogen bonding was a special type of dipole. You need that very electronegative element bonded to it, right? So this is just nonpolar, right? And so that means that the only forces possible are what? Like London dispersion forces, right? So London dispersion forces are the only forces. All right, so we'll leave it right there for now. We're not going to rank it necessarily just yet, but we know this only has London dispersion force. So probably it's going to be on the lower end no matter what. All right. What about H2S? What does that molecule look like? What's the Lewis structure for that look like? It's a bent molecule, right? And is there any other molecules that it looks like that are also up there? It looks like water, right? So sulfur and oxygen bond very similarly. Why do they bond similarly? They're in the same group, right? They're both in group 6, which means that they bond very similar to each other. So sulfur, or sulfur dihydride, is going to look something like that, right? It's a bent shape, which means that we know that it's going to be what? In terms of properties. It should be polar, right? So this is going to be polar, which means it'll have what intermolecular force? Yep, it'll be dipole-dipole forces because polar molecules have permanent dipoles, so you have dipole-dipole. forces. And then what other intermolecular forces is going to have? London dispersion forces. And why does it have London dispersion forces? Because everything has London dispersion forces, right? Just because we're polar doesn't mean that we just get rid of the London dispersion forces. Those are always there. It just means we have both of these now that are present. And we also have hydrogen in this molecule, so why don't we have hydrogen bonding? Yeah, it's not fun, right? So this isn't fun. It's a boring molecule, so it doesn't have hydrogen bonding involved as well. Okay, so that's sulfur dihydride. What about water? What does water look like? It looks exactly the same because they have the same number of valence electrons, right? So this is a bent shape. This is also going to be a bent shape, which means it'll also be what kind of molecule? Polar. And what else? What other? So what forces is it going to have? It'll have. Yeah, this one has hydrogen bonding. So why does this have hydrogen bonding? Because we have oxygen bonded to hydrogen, right? You need hydrogen and oxygen bonded to each other to have hydrogen bonding. What does that mean? If we have a molecule like this that also has oxygen and hydrogen, this does not have hydrogen bonding. So what was this molecule again? Does anyone remember? That was formaldehyde, right? So I was hoping Tiffany was going to remember that, remember that one. But that's formaldehyde, right? Formaldehyde has hydrogen and oxygen as well, but they're not bonded to each other, so it's not possible for this molecule to hydrogen bond. You need them bonded to each other. So this one has hydrogen bonding. It has dipole-dipole because it's polar. And what else does it have? London dispersion forces because everything has those, right? So we have almost all of the molecules done now, right? Only thing we have left is methane, which is CH4, right? So what does the Lewis structure for CH4 look like? It's a tetrahedral structure, right? We just have hydrogen bonded to each of these. This means tetrahedral. If I ever don't feel like writing it, that's what T sub H means. If you ever see that somewhere, I'll usually write tetrahedral. But it's a tetrahedral structure. And so that means the molecule is going to be polar or nonpolar. Nonpolar, right? Because we have the same bond in each direction, right? So that's a nonpolar molecule. So they're pulling in equal and opposite directions. So they all cancel out, all the little dipoles. In general, though, hydrogen and carbon, a carbon-hydrogen bond, if you looked at the electronegativity values, they have the same value. So that's also considered a nonpolar bond. All right, so this is nonpolar, which means that what forces is this going to have? Only London dispersion forces, right? Because it's not polar, there's no dipole-dipole forces, and there's no hydrogens bonded to fluorine, oxygen, or nitrogen. So now we have all of the molecules, all of their intermolecular forces, and now we can use that to analyze the boiling point. So what do you guys think is going to go after potassium bromide? What will be the second strongest, or the second highest boiling point? H2O, right? Because it has London dispersion forces, dipole-dipole, and hydrogen bonding there, right? So it has all of the potential covalent intermolecular forces, right? So H2O should go second. What about after that? H2S, because methane, CH4, and H2, hydrogen gas, those are only London dispersion forces, right? Whereas H2S at least still has dipole-dipole interactions and London dispersion forces. And now we have two molecules that we're left with, right? All we have left is methane and hydrogen gas, right? And they both only have London dispersion forces. So how are we going to distinguish between them? So the shape isn't necessarily going to help us here because the shape is just going to tell us if they're polar or nonpolar again. And we already know that they're nonpolar from the Lewis structure. what increases London dispersion forces? The molecular weight, right? The more electrons we have in the molecule, the more London dispersion forces there are, because they can slosh around a lot more, right? So which one of these is the bigger molecule? CH4, right? So that's how we're going to separate molecules that are nonpolar and only have London dispersion forces, is we look for what is going to be the bigger molecule. So that means CH4 is going to have a higher boiling point, and then hydrogen gas will go last. Right, so this is a relatively simple question in terms of what it's asking, but the level of understanding to be able to answer this is relatively in depth, right? We have to be able to read the chemical formula to understand what atoms are involved in this molecule. Then we have to draw the Lewis structure, and even before we draw the Lewis structure, we have to determine is it an ionic or covalent compound, which we know ionic compounds are between what two types of atoms? Metal and non-metal, right? Potassium is a metal, bromine is a non-metal, whereas covalent compounds are between two non-metals, right? Then once we have that it's covalent compound, we draw the Lewis structures for them, so we have to know how these atoms are connected to each other. Then once we know how they're connected to each other, that tells us about the shape, right? Which we get from the Lewis structure, because we have to know the bonding pairs and the non-bonding pairs, and how those arrange themselves around the atom. And then we use that to determine the intermolecular forces. And once you have the intermolecular forces, then you can rank things in terms of boiling point. All right, so this is a very comprehensive question in terms of everything that we've talked about in the last 3 weeks or so. All right, so there is a lot of information in this. So any questions on that? Or at any point where you guys, I'm completely lost how you did this step.
We said again that CH1 is number 4 because it's larger than H2.
Yeah, it's a larger molecule than H2, right? And so what we're talking about there is it has a larger molecular weight. And today when we talk about the idea of the mole, we'll see how we get molecular weight from the periodic table. But we know that H2 only has 2 hydrogens. CH4 at least has 4 hydrogens. So it already has more hydrogens there, so we know it has to be a bigger molecule. And it's the same thing with atomic size. If you get to a larger atom, there's more electrons because you increase as you go from period 4 to period 5. You add another shell of electrons, more potential van der Waals or London dispersion forces. All right, so that's how we separate those two. We look for which is going to be the larger or smaller molecule in that case.
Can you explain bond one more time, please?
Bond, so hydrogen bonding, right? So hydrogen bonding is when we have a special type of dipole where you have a big electronegativity difference between hydrogen and the 3 most electronegative elements: fluorine, oxygen, and nitrogen. Right? And because the electronegativity difference is so large, and because hydrogen only has 1 electron, right? Those atoms are going to pull the electron. Not going to completely transfer the electron, but they're going to basically make it so that there's almost no electron orbiting around hydrogen at all in a covalent bond. So that means it's going to create a very large permanent dipole in that bond. When you have this very large permanent dipole, that means this partial positive is very partially positive next to another molecule that also has hydrogen bonding involved. That's going to be very partially negative. So those two feel very strong attraction to each other. What that means is in terms of Lewis structure is you just need to have a bond from a hydrogen, right? Hydrogen can only have how many bonds? 1, right? So that means you only need 1 bond between the hydrogen and either fluorine, oxygen, or nitrogen. Fluorine likes to form how many bonds? Has 7 valence electrons.
So 4?
Not quite. It also only likes, halogens also like to only form 1 bond. I know it's a counterintuitive, right? Because one only has 1 valence electron, the other has 7. How do they have the same? But it's because if we draw out the Lewis dots for them, right, only needs 1 more to fill its octet, right? So that means that the only molecule you're going to see hydrogen bonding involved with fluorine is hydrogen fluoride. That's the only molecule you'll see hydrogen bonding, which means that these two are the important two elements for hydrogen bonding. You need a hydrogen bonding to one of those elements. You?
Can you explain the London dispersion force?
Yeah, so these are the forces between nonpolar molecules, right? So again, polar molecules means that when we have, for example, in H2, we have that in the covalent bond, the electron is shared equally between them, right? In this bond, the electrons from each atom are shared equally. When this molecule gets close, right? So electrons aren't static things, right? Remember, we have this weird interpretation. They're waves that are kind of sloshing around in this probability region around the nuclei. It's a fancy way of saying you can just imagine it as kind of like a jelly-like substance that's moving around the nucleus of these atoms. The jelly is negatively charged, so when it gets close to another nonpolar molecule that also has negatively charged jelly around it, it pushes it, it moves it over to one side, right? It only does that for a little bit before it kind of bounces back, the same way when you drop a ball, it'll bounce back, but then it'll eventually come to a rest. When this gets close to another atom or molecule, all the extra negative charge here pushes the electrons in the molecule that's next to it over as well. Then a little bit of time passes, and they slosh back in the other direction, and they go back in the other direction. Right? Now this positive charge is attracted to that negative charge. And what happens is you get this, we would say like synchronization, meaning they kind of sync up like that. And when they sync up like that, that movement of electrons causes a force of attraction between them. And so it's actually, relatively complicated to show that this is a real thing that happens. But it is something. This is the predominant force for a lot of biological processes, like how membranes assemble in your body and stuff. But it's this temporary dipole, right? It's not permanent because there's not a permanent electronegativity difference between the atoms. But it's temporary because it's just caused from a temporary movement of the electrons. And I'm not going to test you guys on that. The only thing, I'll expect you guys to say is, well, it's a temporary dipole which causes an attraction between them.
Right, so if the LDF is present, then that means there's a dipole as well?
It means there's a transient dipole, so it's not permanent. Transient means just it's a temporary dipole, meaning that dipole only exists for a very short period of time.
Okay. How did you find the dipole and the LDF in the example?
So in this one, so the way you find whether that's present or not is you determine is the molecule polar or non-polar, right? So the key thing to remember is London dispersion forces, all you need for that to exist is electrons. They just have to be there. So every single atom, every single molecule in existence has London dispersion forces because they have electrons. So that's why all of them have London dispersion forces, no matter what. For a nonpolar molecule, that means that's the only force they have because it doesn't have a permanent dipole in them. We go to H2S, after drawing the Lewis structure, finding that it's a bent shape, that means that it has polar properties. This is a polar molecule. What does it mean for it to be polar? It means there's a permanent dipole. Right, so we still get this temporary moving of the electrons, but now instead of, if I was to draw the little electron clouds for everything, for H2, it looked like this. For H2S, the electron cloud looks something like that, right? Which means that even though this sloshes around back and forth a little bit to create the London dispersion forces, you also have this permanent dipole going in that direction. And it's like, okay, well then how do I know that this is hydrogen bonding? Well, this is just a very special type of very strong dipole, which is why we classify it on its own. And we know that because the hydrogen is bonded to the oxygen.
So if it's non-polar, it's temporary, but if it's polar.
If it's polar, what that means, saying you have a permanent dipole is the same thing as saying it's a polar molecule. Does that make sense to you?
Yeah, it makes sense.
All right, cool. like I said, it's a lot of, I know it's a lot of information just for one seemingly simple problem, right? There's a lot of thinking that goes into it. And obviously on an exam, I wouldn't expect you to show all this, but this is what you want to realize as you're looking at this. Eventually you'll get to the point where you look at those molecules and say, well, those two are nonpolar, and you could just rank them without even drawing out everything, just because you'll have done it so much at that point. All right. Any other questions? Let's see, what was the next example? All right, so this one is related to one of the exam questions, so we can talk about that. So now that we've gone through this, we've done this with a bunch of different molecules, determine the shape and the intermolecular forces that are present in HCN, right? So this is one of the Lewis structures that was on the exam last week. See if you guys can figure out the intermolecular forces. I'll give you 3 minutes to figure it out, right? So what is the shape for this molecule before I draw the Lewis structure? What do you guys get? It should be linear. And how many bonds are there to carbon in this molecule? There's 2 bonding pairs and 4 total bonds to each of them, right? And what the structure is going to look like is something like this, right? So I saw a good number of you guys get this on the exam, which I was pretty happy with because we hadn't, looked at anything like that. That was kind of the one part of that problem that was the challenge problem. But this is a linear molecule, right? We have 4 bonds to carbon total, but only 2 bonding pairs, which means that it's linear. So we know that linear molecules are generally what type of polarity? They're usually nonpolar, right? But is this molecule polar or nonpolar? This one should be polar, right? And why is it polar and not nonpolar? Because we have unequal sharing on both sides of the linear molecule, right? Nitrogen is very electronegative, and this bond in general is going to be relatively nonpolar, right? Which means that there's going to be a dipole that's not being canceled out in the other direction. So hydrogen and carbon, those form a nonpolar bond, so those don't share electrons unequally in any way. But the nitrogen is going to be pulling a lot of electrons from carbon. So that means that you're going to have a net dipole in this molecule. So what forces are going to be present? What do we know is there for sure no matter what? London dispersion forces are always going to be present because that's in everything that has electrons. And what else is going to be present? Dipole, because we have a permanent polar molecule, or a permanent dipole in the molecule, which makes it polar. And the only other one we can have is hydrogen bonding. Do we have hydrogen bonding here? No, we don't, because the hydrogen is not bonded to what? Yeah, it's not bonded to the nitrogen in this molecule, which means that it can't be hydrogen bonding. So even though the chemical formula looks like there may be hydrogen, because we have hydrogen, carbon, and nitrogen, once we draw the Lewis structure, we see that they're not connected, so we can't have hydrogen bonding, right? So there's no hydrogen bonding. Right, and I'll write H bonding a lot of times to mean hydrogen bonding. All right. So how do you guys feel about that example? The other one is a lot harder, but this one is just looking at one molecule. Thumbs up, thumbs to the side, thumbs down. Thumbs down? Okay, so we'll have more practice on that on the next problem set, which I'll probably give you guys later this week, actually. All right, so we're gonna shift gears a little bit. So we've talked about all these properties and kind of qualitative measures of understanding molecules and the forces between them. We're gonna kind of move back towards things like unit conversions and determining mass from chemical formulas of molecules, and then determining mass that's created or destroyed in chemical reactions. And that's gonna kind of be the focus for the next exam, right? So unit conversions are gonna come back pretty strong. This last exam was a nice little break from things like unit conversions. But if you're math-minded, you'll probably be a little happier because they're gonna be moving back towards math. But a lot of it is going to be unit conversions, not necessarily hard algebra, right? So I know the equations